Hello everybody. In this video, we'll be talking about partial derivatives. It's the multivariable version of differentiation, which you probably learned back in Calculus 1. Recently, we've been talking about functions, say a function f, which has two real numbers as input and one real number as output. Often we might write this in the form f of x comma y is equal to z. So for example, we might have the function, let's say we could do z equals x squared times y cubed, or we could do another function. And we could write z equals sine of x times y. There are lots of variations on functions that you can write. So what we'd like to do today is learn how to calculate derivatives when there's more than one variable present. You might remember from Calculus 1, so we'll go do a little blast from the past in perhaps a different color. Right, we would define for a function f of x equals y, we would define the derivative df dx, or we might also write that dy dx, to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Sometimes I actually like to write this in a different way to remind us that it's actually a difference quotient. And it's really like a slope formula, right? You have difference in y's or difference in outputs on the top here, and you have difference in x's on the bottom here, and you're letting letting h get closer to 0, which means these two values are moving closer and closer. But of course, it's easiest to simplify this on the bottom. The x and the negative x cancel, leaving us with just h. Now, we can make the same definition in multivariable mathematics if we have a function which has more than one parameter. But here, the plus h, right, this h that we're adding on to, we can add that to either the x or the y component. And so we could say if z is equal to a two-variable function, f of x, y, we can define the derivative of f with respect to either of these two variables. And we'll often write this using kind of a curly d. We can define the derivative, that's the derivative of f, but now we have to say what variable is on the bottom here. Right? We have an x down there. So we'd say the derivative of f with respect to x. We could define that kind of the same way we would define it in Calculus 1, and say this is f of x plus h comma y minus f of x comma y all divided by h. So in this case, one of the things I'd really like to draw your attention to is we have this dx on the bottom here. That indicates that the x is being added to the h is being added to the x component, right? X is changing here. The y in both of these cases, right? We've got a y here and a y here. The value in the y position is not changing, right? So x is changing. X is kind of our variable, meaning it's able to vary the value in that position. The y component here, y is actually like a constant. And so y is constant. In other words, we're not interested in the change of y in this expression. Right here, we're looking for the change in f as x changes. We could make a similar definition if we wanted to learn about the rate of change of f with respect to y. And this would still be defined in a similar way. The limit as h goes to 0, f of x, comma, y plus h minus f of x, comma, y, all divided by h. So you can define different derivatives. And as we'll see in a future lesson, these give you slopes of tangent lines, where the tangent lines are parallel to either the x-axis or the y-axis. In fact, there's lots of tangent lines to a multivariable surface, but that is a topic for a different day. Right, so practically speaking, you know a lot of differentiation rules for polynomials, you know, differentiation rules for trigonometric functions and exponential functions, you know, combinations of functions like the sum rule, the product rule, the quotient rule, the chain rule. A lot of those apply in multivariable calculus as well. And so given that z is a function of x and y, right, how do we calculate, practically speaking, how can we calculate something like df dx? I say d, even though I'm using this curly d, which equivalently I might write that as dz dx. And how do we calculate the derivative df dy, which we might also write as dz dy? And the answer is to think of one of the variables as a variable. One of the variables is changing. Sounds redundant, I know. And think of the other variable as being held constant. Right, so in both of these cases, right, we'll think of this variable. Let's say think of this letter as variable, and the other as a constant. Again, for inspiration, I'd like to go back to Calculus 1 for just a moment. Right, in Calculus 1, if I had the function y as a function of x, if I did something like 10x cubed, you would know right away, right, that the derivative of f with respect to x, well, using the power rule, we would know that that's 3 times 10x squared, which we'd probably write as 30x squared. And similarly, if I did a variation on this, if I said instead that f of x was the function, I don't know, c times x to the 5th, right, where c is some constant, you would apply the same rule and find out that df dx is equal to 5 times cx to the 4th. Because in your mind, you know that this letter represents a constant. So here in multivariable mathematics, you know, we're going to know that one of our letters will be treated as a variable and the other will be treated as a constant. So let's do an actual example next. Let's say z is a function of x and y. Let's say it's x squared times y cubed. And let's say we want to calculate df dy. Even I sometimes forget to write those curly d's. If I want to calculate this derivative, I'm going to think mentally, put a little note down here, I'm going to think of x as a constant. And so over here, in fact, I don't just have x, I have x squared, right? But if x is a constant, x squared is a constant. So think of this as some constant times y cubed. Right? The derivative of a constant times y cubed is 3 times that constant times y squared. But here the constant is x squared. So the answer, the derivative of x squared y cubed, the derivative with respect to y, is 3x squared y squared. Similarly, let's do the f dx. Right, in this case, I'd like you to think of the letter y as representing a constant. In this case, it's x which is changing. And so here we have x squared times a constant. Right? We know what the derivative of x squared times a constant is. It's going to be 2x times that constant. So here I have 2x times the constant, which is y cubed. So the answer here is 2xy cubed. And that's all there is to it. Sometimes it can be a little bit tricky remembering what's a constant and what's not. We have to remember to apply our other rules as well. So maybe let's do another example. I'll fit in a little example over here. Let's switch colors for fun. Let's do as an example z equals f of x comma y is equal to, I don't know, let's do maybe 4x plus 5y. In this case, I'll use the other notation just for practice. What's dz dx equal to? Right, in this problem, again, looking at our derivative, this notation, the fact that we have an x on the bottom says that x is our variable, right? And we're going to think of y as a constant. So here, think of this expression as 4 times x plus a constant. The derivative of 4 times x is 4, plus, might be tempting to say the derivative of 5y is 5, but if y is a constant, 5 times y is also a constant, and the derivative of a constant is 0. So that's actually it. That's the derivative. dz dx is equal to the constant 4. And of course, we're also going to calculate dz dy. And again, the dy on the bottom tells you that y is the variable in this exercise. If y is the variable, then x is a constant, and 4 times x is a constant. So now this problem is asking for the derivative of a constant plus 5y. The derivative of the constant 4x is 0. The derivative of 5y is 5. That's kind of interesting. It's got 2 constant derivatives. And one reason to think of why that might make sense for this problem is the original equation was z equals 4x plus 5y, but I could actually rearrange this in the form 4x plus 5y minus z equals 0, which is the equation of a plane. You might recall a plane, mathematics, is just a flat surface with constant slope in each direction. Just like a line has constant slope in 2 dimensions in algebra or in calculus 1, here we have a plane which has constant slopes in both directions. All right, let's do some more examples. Let's do one which maybe involves a product rule. Or maybe that appears to use a product rule. Let's try. Oh no, here's a good one. Let's do this. Let's do z, again, a function of 2 variables, f of x comma y, is equal to x times sine of y. Right, this, at first glance, looks a lot like a product rule because it's the product of two functions. But what if we want to calculate the derivative dz dx? Remember, this notation means that x is the variable and treat y as a constant. The x on the bottom means you have x times sine of y. And y is a constant. Sine of a constant is also a constant. So this function is truly x times a constant in the context of this problem. The derivative of x times a constant is just that constant. So the derivative here is dz dx equals sine y. Similarly, we should calculate the derivative dz dy. It might be tempting to think that, these problems are symmetric and y is the variable and we can just drop this out. Let's think about this for a moment. We have dz dy. The y tells us that y is a variable and x is a constant. So this function, in this context, is a constant times sine of y. The derivative of a constant times a function is the constant times the derivative of that function. And so this is going to be x times the derivative of sine y, which is cosine y. And those are the two partial derivatives in this case. They're called partial derivatives because they each give you part of the information about how the function is changing. Okay, let's do one more example of partial derivatives. Let's see. Let's do z equals f of xy is equal to x times sine of xy. And here, I'd like to start off by calculating dz dx. So again, here we have x as our variable, and that tells us we can think of y as a constant. And so in this case, we have a function of x times another function with x in it. Right, so the key part here, unlike the previous problem, where we had an x times a constant, here we have an x, we have a function of x times another function involving x. So here we actually need to use the product rule. Right? You might remember the product rule says that we're going to have the derivative of the first times the second plus the first function times the derivative of the second function. Right, so here we're using product rule. Make a little note. We'll use the product rule because we have a product of two functions of x. Right, so we have the derivative of the first function times the second function plus the first function times the derivative of the second function. But here we have a function within a function. Right? We have a sine function on the outside, and then we have multiplication by y on the inside. Right? So here we actually have a chain rule in the second part of this. Oh, this is a good problem. So to start off, we do the derivative of the outside function applied to the inside times the derivative of the inside function. Right? And again, y is like a constant. The derivative of x times a constant is just the constant. Right? So here, we use the chain rule here. All right, so that's dz dx. Will dz dy be as hard to calculate? Well, let's see. First, you might ask yourselves, do we need to use the product rule again? Well, do we have a function of y times a function of y? In this case, we have a function, but it's a constant function, right? For dz dy, y is the variable. So we have a constant times sine of xy. So we don't need to use the product rule for this particular problem, right? The derivative of a constant times sine of xy is going to be that constant times the derivative of sine xy. Now, sine of xy, in this circumstance, there's another chain rule there. We have a function on the outside. Remember, y is your variable. The outside function is sine, and the inside function, what are we doing to y? We're multiplying it by x. So again, we're going to need to use the chain rule here. And so again, we're going to use the chain rule to figure out what this is. Well, first, the derivative of the outside function, cosine of xy, times the derivative of the inside function. So y is the variable. We have a constant times y. The derivative of constant times y is that constant. So in this case, we have x times cosine xy times x. Just I feel like I need to rewrite that. I can gather together the x's. That'll give us x squared times cosine xy. If you wanted to, I guess you could rewrite the first one if you want. You could make it a little bit simpler. You could rewrite that as sine xy plus gathering the x and the y out in front of that second term. That'd be xy cosine xy. Very good. And those are partial derivatives. Now, as I often like to say, I feel like I haven't said this lately, you learn math by doing math. I should give your hand a try at this problem. And so I just like writing this down. You learn math by doing math. So try this. Go ahead and kind of review your knowledge of derivatives in the context of multivariable calculus. Let's say z is a function of x and y. Let's see, let's make something interesting here. Let's do cosine of x squared. Let's try x cubed plus y to the fourth plus x to the fifth. And go ahead and try to calculate. Find the values of the derivatives dz dx and dz dy. Right, there might be a little bit of maybe a chain rule in here. You've got functions inside functions. Just keep in mind what's a derivative and what is not. All right, good luck.